What specific problem does the MovieDreamer method aim to solve in the context of long video generation, and how does it differ from existing approaches?
The MovieDreamer method specifically aims to address the challenge of generating long videos with complex narrative structures and intricate plot progressions, which existing approaches struggle to achieve, particularly when merely scaling current methods. Unlike predominant video generation techniques that focus on short-duration content, MovieDreamer integrates autoregressive modeling with diffusion-based rendering to ensure both long-term narrative coherence and short-term visual fidelity. This hierarchical approach allows for the prediction of visual tokens that maintain global consistency in key movie elements, such as character identities and cinematic styles, even during complex scene transitions. Additionally, it employs a novel multimodal script that enhances narrative continuity and character control, setting it apart from traditional methods that often lack flexibility and coherence in longer formats. Overall, MovieDreamer significantly extends the duration of generated video content while preserving high-quality visual details and character identity, outperforming existing models in generating visually stunning and coherent long-form videos.
How does the proposed MovieDreamer method work? Please illustrate the process step by step, detailing the roles of the autoregressive model and diffusion rendering.
The proposed MovieDreamer method operates through a hierarchical framework that integrates autoregressive modeling with diffusion rendering to generate long-form videos. First, it utilizes a multimodal script that includes detailed descriptions of characters and scenes, which serves as input for the autoregressive model. This model, initialized from a pre-trained Llama 7B, predicts compressed visual tokens in an autoregressive manner based on the script and historical data, ensuring long-term narrative coherence. Next, these visual tokens are decoded into keyframes using a diffusion autoencoder, which compresses the images into a reduced number of tokens while preserving essential details. Finally, the keyframes are rendered into video sequences using an image-to-video diffusion model, enhanced by an identity-preserving diffusion decoder that mitigates errors in visual token prediction and maintains character identity throughout the generated video.
What are the theoretical or practical benefits of integrating autoregressive modeling with diffusion rendering in MovieDreamer?
The integration of autoregressive modeling with diffusion rendering in MovieDreamer offers several theoretical and practical benefits. Theoretically, this hybrid approach allows for long-term narrative coherence, as autoregressive models excel in maintaining consistency across complex storylines, while diffusion rendering ensures high-quality visual fidelity in the generated frames. Practically, this combination enables the generation of long-form videos with intricate plot progressions, overcoming the limitations of existing methods that struggle with either short-duration content or visual quality. Additionally, the use of a multimodal script enhances character control and identity preservation, allowing for personalized content generation that aligns with user preferences. Overall, this synthesis results in a robust framework capable of producing visually stunning and contextually rich videos that maintain both narrative integrity and visual detail.
How was the effectiveness of MovieDreamer validated in the experiments, including the types of datasets used and the specific evaluation metrics employed?
The effectiveness of MovieDreamer was validated through extensive experiments on a test dataset consisting of 10 long movies that were not included in the training set, yielding 50,000 keyframes after pre-processing. Each keyframe was processed through a proposed data pre-processing pipeline, which accurately extracted and annotated keyframes, generating corresponding textual prompts and character face embeddings. The evaluation metrics employed included the clip score for assessing semantic alignment between the plot and generated outputs, as well as quality metrics such as aesthetic score, as Frechet image distance, FID, and inception score, IS. Additionally, consistency was measured using short-term, street, and long-term, LT consistency metrics, which evaluated the presence of target characters across frames. The results demonstrated that MovieDreamer achieved high scores in both LT and ST consistency, along with superior quality metrics compared to existing methods, showcasing its capability to generate coherent and high-quality long-form videos.
What specific results were achieved by MovieDreamer in terms of video generation quality, coherence, and consistency? And how do these results compare to state-of-the-art methods?
MovieDreamer achieved significant advancements in video generation quality, coherence, and consistency, particularly in generating long-form videos that maintain both short-term and long-term character consistency. The method demonstrated superior performance over state-of-the-art models like story diffusion and StoryGen, which struggled with maintaining character consistency and coherence across frames. Quantitatively, MovieDreamer scored high in long-term LT and short-term street consistency metrics, as well as in aesthetic quality measures such as the Inception score as, aesthetic score as, and Frechet image distance, FID. The qualitative results showcased the model's ability to generate visually stunning and coherent long videos, lasting hours with minimal quality compromise. Overall, MovieDreamer not only excelled in generating high-quality images, but also effectively preserved character identities and narrative continuity, setting a new benchmark in the field of video generation.
What limitations or challenges does the MovieDreamer approach face, particularly in relation to computational efficiency or generalizability of the model?
The MovieDreamer approach faces several limitations and challenges, particularly regarding computational efficiency and generalizability. Firstly, while autoregressive modeling excels in handling complex narrative structures, it is not as compute efficient as diffusion models for visual rendering, requiring significantly more computational resources even for image rendering. Additionally, the model's reliance on a limited dataset of 50,000 long videos poses a risk of overfitting, as the high-quality training data is scarce, which can hinder the model's ability to generalize effectively during testing. To combat this, the authors implement various anti-overfitting strategies, such as aggressive dropout and data augmentation, but these may not fully mitigate the risks associated with limited data. Furthermore, the model's performance can be sensitive to the quality of the multimodal scripts used for conditioning, which may affect its ability to maintain narrative continuity and character consistency across diverse scenarios.